the rational functions toolbox, have this out. You may want to take the state log if that helps you go through this. This is important. The end behavior of a rational function is affected by the numerator and the denominator with the greatest degree. It's a lot of terminology there. So numerator and denominator, we know what that means. Degree means the highest value of the exponent, in this case in the numerator and the denominator. And they're saying the end behavior of a function is going to be determined by that. Let's go to the next page. So this is discussing straight the degree, so please circle the word degree. We're discussing the degree here. So when we have an example here where we have the numerator, the degree of the numerator is less than the degree of the denominator, let's do a quick example of that. Let's say f of x equals x to the second minus 3, I'm just making this up, x to the third plus 2x plus 3. Oops, that's a crazy 3. So here we have a function, and so if we concentrate on the degree in the numerator and in the denominator, we can see the degree of the numerator is less than the degree of the denominator. Well, what happens when that's the case? When that's the case, we have a horizontal asymptote of y equals 0. A horizontal asymptote of y equals 0. And how it impacts the end behavior is as you go to the far left, it approaches 0, and as you go to the far right, it also approaches 0. So let me just make up an example. Let me go here to, so I gave us an example where we had a degree of 2 in the numerator and a degree of 3 in the denominator. And that's all we're looking for. We have the degree in the numerator is less than the degree in the denominator. And in that case, if we come back to this, we can see we do have right here along this line of the x-axis, or y equals 0, if I do that, y equals 0, we can see that that is going to be our horizontal axis. So on the far left and on the far right, we can see it approaches y equals 0 to the far left and it approaches y equals 0 to the far right. Will that always be the case? It will. And so that's this first rule that we just discussed. Now, what happens when they're equal? What are they talking about being equal? They're talking about the degree. So I can come up with any example here. Let's say x squared minus 2x plus 5 and x squared plus 3x plus 4. Completely making those things up. I'm going to come back over here. Let's save ourselves some time. Let's save ourselves some time. Press. So if this is the case, and we're going to look in Desmos in just a second, if this is the case, what it says is that we are going to have another horizontal asymptote, and that's determined by taking the leading coefficient of the numerator and dividing it by the denominator. And then the end behavior, as we go off to the far left, it approaches that value, and if it goes off to the far right, it approaches it. So I plug this particular, just a second here, just dropped the cap of my highlighter. I plug this particular example in. Let's go look at it. And now I can see the leading coefficient of the numerator and the denominator is 1 over 1. So if I write y equals 1, we can see that as I go off to the far left, it's approaching that line. As I go off to the far right, and especially if I zoom out here, you can see as you go off to the far right and far left that it is approaching that horizontal asymptote. Now let's just change this up so we can see here. If I just change this up and make this a 4 and let's make this a 7, well, now I need to change that. So now this will be 4 divided by 7. And even when I zoom in here, you can see as it approaches the far left and the far right, it's going to be the value 4/7 that it's approaching. Let's go to the next one. Let's now show an example where the numerator is greater than the denominator. So let's go h of x is equal to numerator is greater than denominator. So x squared plus 1, and this is going to be x minus 2. So the end behavior is similar to the quotient of the two polynomials without a remainder. And what that means here is that we have a slant asymptote. If you can write that down, slant asymptote. So you're going to do polynomial long division. You're not going to worry about what the remainder is when you do it, but what you have on top. So when we do long division and we divide what we have on top, we're going to write y equals whatever is remaining, and that will be the asymptote. That will be the slant asymptote. So let's take a look and just see what this would have. So here we have a 2 on top, a 1 on the bottom, so the numerator is greater than the denominator. Okay, so for that situation, I need to put the numerator in here, but notice how there's a missing term in the middle. So that needs to be plus 0x plus 1. That missing value needs to be accounted for. On the outside is x minus 2. Now I'm going to do polynomial long division here. So x times what gives you x squared? That would be x. So I've got x squared minus 2x. Now I change the signs and I add straight down. Additive inverses, bring down the 1. X times what equals 2x? A 2. Multiply to get 2x minus 4, change the signs. And what this says is, hey, we don't care about, what this says is, hey, we don't care about the remainder. This is all we're going to be concerned with. So I'm going to press pause, and what I'm going to do is I'm going to graph this, and then I'm going to graph y equals x plus 2 to see if we can noticeably see on the graph that it is